Hello again, everybody. Welcome to chapter 2.2. This one is looking at water in specific. When we're talking about the chemistry of life, you really need to know about the properties of water because life would not exist without water, and it impacts life in so many different ways. Before you watch this, make sure that you watch the biological molecules of, building blocks of molecules, that's what it's called. Make sure you watch the building blocks of molecules. That introduces the idea of water being a polar molecule, which is important to know before we start this. So we talked about last time in that previous lecture that water is polar. So here's a water molecule, H2O, and the electrons tend to hang out around the oxygen more than the hydrogen. So oxygen gets a negative charge, while the hydrogens develop a positive charge. This is called a polar molecule. Water is the standard polar molecule. As we discussed previously, if something does not have these positive and negative regions, no positive or negative, then it is said to be a non-polar molecule. And the example that we used was oils. Oils don't mix with water. The thing that we talked about mixing with water was sugar, because sugar is also polar. So water is polar, and polar dissolves other polar molecules. That's the way that it works. So sugar is polar just like water, which means if you dump sugar into water, it'll dissolve. Anything that dissolves in water is said to be hydrophilic. Hydro means water, philo means love, so philic means water loving. If something dissolves in water, it is said to be hydrophilic. And just to be clear, if something is polar, it's going to be hydrophilic. It's going to dissolve. If something has these positive and negative regions, just like water, when you mix them, they're going to attract to each other and dissolve. So polar equals hydrophilic. Sugars and salts are two familiar examples, which we've talked about. The opposite of hydrophilic would be hydrophobic. A phobia is a fear. So hydrophobic means water fearing. And basically it means you don't mix with water. And just like we did with polar, non-polar also has a synonymous meaning with hydrophobic. Oils and fats, those are non-polar hydrophobic molecules. Hydrogen bonds, I hinted at those in the last lecture, so now let's talk more about them. Take a look at this beautiful picture up here. Oxygen is negative, hydrogens are positive. Any body of water, even a glass of water, is going to have uncountable numbers, so to speak, of individual water molecules. And they're going to be attracted to each other. The positive hydrogen on one water molecule is attracted to the negative oxygen on another. That's going to happen amongst all of the water molecules within a particular body of water. Neighboring water molecules are attracted to each other because of the negatively charged oxygen and the positively charged hydrogen. That is a hydrogen bond. So a hydrogen bond is different from covalent bonding in that covalent bonding involves actually sharing electrons, and that's what holds the water together. But neighboring water molecules have these weaker bonds called hydrogen bonds that forms between the positive and negative regions of the water. So, why does this matter? Well, life needs water, and several of the properties of water that life needs exist because of this hydrogen bonding. And we're going to start off with the property of ice floating. So let's see here. Do I have a picture? Yeah, there we go. Up here we've got ice and liquid water. Now, normally speaking, a solid is more dense than a liquid for a particular molecule. Because in a solid, the molecules themselves should not be moving, which means there needs to be more of them, more tightly packed. It should be more dense. In a liquid, the molecules are still moving around. It should be less dense. Just to rehash what density is, it's the amount of mass you have over how much space you take up. So, 40 pounds distributed over this much space, it's going to be a lot less dense than 40 pounds in this little tiny space. All right, density is how much mass you have relative to how much space is taken up. So, normally a solid should be more dense than a liquid. In water, hydrogen bonds cause the molecules to stationarily remain in this lattice structure. There's a lot more open space here. It's a lot less dense than when it's cold water and all of the water molecules are still moving around. Ice, solid ice, less dense than cold water. Why does that matter? It matters because ice floating creates an insulating layer atop of lakes and ponds. Cold air can only penetrate so far. You get a nice layer of ice. The water below is shielded from the cold air above. Aquatic life can persist. Fish can continue to swim. Turtles and frogs can burrow themselves into the mud at the bottom and go dormant for times. Ice floating prevents complete deep freezes of water, which in Missouri we don't really get cold enough for that to be a huge phenomenon that we think about, but I grew up in Minnesota where it gets very cold and this absolutely would kill off a lot of life in some of the lakes and ponds up there if ice didn't float. Also, polar bears feed on the sea ice, feeding on seals and such. So ice floating is pretty important to them as well. But this is quite important for aquatic life, to have ice floating. Other properties of water caused by hydrogen bonding include heat absorption, which keeps the temperature of air around water much more moderate. Oceans, for example, absorb a lot of heat, which keeps the surrounding air temperature much cooler. If you go look at the weather for San Francisco, it's going to be a pretty narrow range of temperatures because of that sea effect. Also, water is used to cool organisms through evaporation and sweating, which works by evaporative cooling, removing heat from the organism. So water is pretty darn important. And a lot of that importance is attributable to those hydrogen bonds. This one's kind of harkening back to what we talked about with hydrophilic, hydrophobic. Water dissolves a lot of stuff because it's polar, and so water is called the universal solvent. Actually, I think this might be written on the slide. Yeah. So if you've got a mixture of things, you're going to typically have something that's doing the dissolving and something that's getting dissolved. And in life, living things are built from cells. Within a cell, you've got what's called the cytoplasm, and it's primarily this jelly-like fluid that is water-based. Water is the solvent. Water is the primary fluid in the cell. Solutes are substances within that solvent that get dissolved. You have solutes within your cells. Right? And sugar and salt are two examples of solutes that would be present in water. Here's a hummingbird. And hummingbirds feed on nectar, which is sugar water. And so they would be feeding on a solution with water as the solvent and sugar as the solute. Just some terms to be aware of. Two other properties of hydrogen bonds, adhesion and cohesion. So adhesion is the tendency of a molecule to bond with other molecules that are different from it. If you want to think of water's adhesive properties, think if you get caught in the rain and you're wearing like a cotton shirt or something, how much heavier it gets. It absorbs the water sticks to it really well. Cohesion is the tendency of molecules of the same kind to stick together. Water is very cohesive. One way this benefits life is it allows water transport to the canopies of tall trees. So trees don't have blood, but they have vessels or channels within their tissue that carry water and other dissolved stuff, kind of like your blood vessels work for you. So trees have a network of vessels that transport water up, down. Water is so cohesive that evaporation can take water away from the highest leaves in the canopy, and along the entirety of the tree, water will move upwards in one cohesive unit through these vessels, which is pretty cool, considering that water starts coming up through the roots. In fact, the power is so strong it counteracts the pull of gravity. So water's properties allow tall, upright growth of trees because it can be transported through those vessels thanks to cohesion and adhesion. All right. I know you've all heard of acids and bases, but you might not know what exactly they are or what we're talking about. So let's start over here on the left, or on the right. Water molecule. You can see the electrons. If you watched the previous lecture, you should be familiar with this diagram. A solution with water as the solvent is said to be what's called an aqueous solution. Okay. So anytime you have an aqueous solution based with water as the solvent, sometimes one of the hydrogens likes to go off on its lonesome, but it leaves its electron behind. So it goes off, like you see here. Since it's leaving its electron behind, and it still has its single proton, it has a positive charge, and it's called a hydrogen ion. The O and the H that are left, they kept the electron, but they're missing that proton that hydrogen took off. So now we've got a negative charge, in spite of having that extra electron. Ignore that sentence. Now we have a negative charge. So we have two charged molecules. Hydrogen ion, this one's called a hydroxide ion. It has that electron left behind by hydrogen. So how does this relate to an acid and a base? An acid is any substance that increases the number of those hydrogen ions in a solution, or, and this isn't up there, an acid can be anything with a greater concentration of hydrogen ions than the alternative, which is hydroxide. So, in an aqueous, water-based solution, if you've got more of these than these, you are acidic. In contrast to that, if you've got more hydroxides than hydrogens, you are a base. What if you're equal? What if it's truly equal in terms of both of those dissociated ions from water? Then you've got a truly neutral solution. Given the size of these, realistically, there's probably no such thing as a truly neutral solution. But theoretically speaking, water is supposed to be around there, pure water. Let's go ahead and take a look at the pH scale. So, pH scale goes from 0 to 14, and you can see the little beaker here with water shows it pretty well how this works, at least in a very easy to understand way. So an acid, more hydrogens than hydroxides, base, more hydroxides than hydrogens. Pure water has an exactly equal number. The higher the numbers go, the more basic or alkaline you are. That's a term you might see. The term alkaline has the same meaning as being basic. So, higher the number, the more alkaline. 7 is pure neutral. Anything below 7 is an acid. Anything above that would be a base. The lower you go here, the more acidic you get. The more acidic you get, the higher the concentration of those hydrogen ions. So just to reiterate, lower pH means more acidic. Higher pH means more basic or alkaline. 7 is truly neutral. Also, just some good information on how the scale actually works. So, pH of 8 seawater is actually going to be 10 times less acidic than water. And you know what? Let's do this in reverse. Pure water is going to be 10 times more acidic than seawater. So every number jump on the pH scale is a 10 times increase or decrease. So pure water is 10 times more acidic than seawater. Urine is 100 times more acidic. This is 1,000. Tomato juice is 10,000. Soda is 100,000 times more acidic than seawater. That means that there's 100,000 times more hydrogen ions than you have in seawater. And so that's how the scale works. It goes by powers of 10. Your body has to maintain homeostasis. If you can remember that term from the first lecture, it means maintaining a consistent internal environment. And so one thing you got to maintain within your body is your pH levels. So a buffer is a substance or pair of substances that minimizes a change in pH. Generally, a buffer consists of a a weak acid and a conjugate base that kind of take in hydrogens and send out hydrogens as needed. Your blood pH needs to be around 7.4. So you can go between 7.35, 7.45, but it has to stay within that range. And so once you start to get too acidic, let's say you're here at 7.35, just remember, the lower the number, the more acidic it is. So let's say your blood starts to get on the acidic side, your buffer system is going to absorb some hydrogens. And if you remember, the more hydrogens you have, the more acidic you are. So if we absorb some hydrogens, you're going to remove them from your blood, which means fewer hydrogens makes you less acidic. So absorb some hydrogens, our blood pH gets down here. Oh, we're getting a little too basic here. Let's release some hydrogens, make it more acidic again. Oh, time to absorb some, and it just goes back and forth. It's a really slick system. It's called the carbonic acid and bicarbonate buffer system. We're not going to get into any more details about the specific molecules that are involved other than giving you their names. But that is an example of a buffer helping to maintain homeostasis within your bloodstream. And that should do it for this overview of water.